Okay, hi everyone. Let's get started. Thanks for coming to today's review session. It's going to be. I'm going to keep this relatively informal, sort of like a question and answer session. I would like to go over any of the questions that you may have on the homeworks, and I also want to tell you a little bit about what's going to be on the test. So we'll kind of do this. I want to start with the questions first. Are there folks waiting for the classroom? Oh, you can stay if you like. No problem. You're welcome to stay. Yeah, you're welcome to stay and take pictures. I was just wondering if folks were waiting for a class or something. Feel free to take pictures if you'd like. Okay. So how about this? We'll start with questions. We already know basically what the test is about, so I want to go over some of the homework questions you may have and some of the conceptual questions. So really quickly, the test is going to be on Thursday. It's going to be 2 hours, 3:30 to 5:30. I'm sorry, 3:30 to 5:20, because there may be a class coming in afterwards to take another final exam. It's going to be the same format as the last tests. There's going to be roughly like 4 or 5 regular questions, 1 extra credit question. Of those 4 to 5 regular questions, you can expect to see a combination of calculations which are similar to the homeworks, and then the conceptual questions, maybe 2 questions worth of conceptual things. Or the conceptual questions may be mixed into the other questions. The topics to be covered in the final exam is the clean room lab. So please do go over that lecture where you learn about the different tools in the clean room and how to fabricate a diode, the fabrication sequence. Also go over the lab. So your pre-lab assignment and your the experiments that I wouldn't say experiments, but the measurements that we took in lab. Make sure that you understand what those measurements are and how we did them. In the past, when I've had questions on the clean room lab, most of them are conceptual in terms of what does a spin coater do? You know, what happens, the longer we keep a wafer in the furnace, how does that change the diffusion profiles? What is the probe station used for? So conceptual questions like that. So the first topic is the here, let me just add this in here. Maybe it'll be helpful if I just jot some of these things down. I'm making this list on the fly, so it may not be completely exhaustive, but it'll give you a general idea of what will be on the test. So the clean room lab, conceptual questions about the tools in the clean room. Let's go here. Bear with me here. Conceptual questions about clean room equipment, how to fabricate a diode, how to how to do let's say measurements of sheet resistivity and what it means. What else? Calculations of sheet resistance and resistances of a semiconductor resistor. understand this goes under the questions about cleanroom equipment, things like photolithography. You can expect some questions about that. Spin coaters. Let's go. Photolithography, spin coaters, photoresist, exposure systems. In other words, a mask aligner. How many of you remember the stuff from the clean room? Is some of these things looking familiar? Okay, good. Yeah. So if you've attended the clean room lab and you got a feel for how they do things, and then you also watch the video lectures, you should be fine. In the thin films bay, things like the sputter coater, evaporator. You know, conceptually, what is thin film deposition? What are you depositing? Let's see. Moving on to the furnaces. What are the furnaces used for? You know that diffusion is one of them. What else is a furnace used for? Diffusion was the most important thing, and diffusion is for doping the semiconductor. There's a couple other things that the furnace was used for. Any guesses? So diffusion is one of them. Oxidation is another one. Oxidation is when we put the wafer in a furnace, silicon wafer, and we put an oxygen gas over it. And there's an oxide layer that forms on the surface of the silicon. The oxide is an insulator. That oxide layer is the oxide layer in the MOSFETs that we talked about in Chapter 6. Right, so that's another important parameter there. How does the furnace temperature and time determine doping profiles? How does doping in a furnace work? Things like that. So in terms of testing and metrology, what are the tools that we looked at in the clean room? What are the testing tools that we looked at?
Probe station.
Okay, probe station is one of them. What else? Let's have someone from the back there. You guys are all like staring at the screen here. What are the other tools that we have that we looked at in the clean room? Yeah? The resistance of the diode? Oh, the sheet resistance. Yeah, what do we use to measure the resistance of the surface of the wafer? What was that tool? Remember we put the wafers on top of the tool and measured the sheet resistance? Did anyone remember what that was called? 4-point probe. Yeah, exactly. 4-point probe. The deck tech, right? Surface profilometer. So that's for measuring the surface topographies, you know, the thicknesses of the layers. Well, we also had a multimeter, but that's not really that. That covers most of the things that we'll be talking about in the clean room. Oops. So these are the different concepts that could be here. be on the exam regarding the clean room. So the next topic is metal semiconductor junctions. And then the third topic will be MOSFETs. Okay, so I was planning on addressing homework questions first, but I think this is helpful, so let's do this. All right, so what are some of the concepts under metal semiconductor junctions? Energy band diagrams. This would probably be the main thing. I would like you to make sure that you are able to draw the energy band diagrams for for all the types of metal semiconductor junctions. So N-type, P-type Schottky barriers, N-type, P-type ohmic junctions. So understand the concept of tunneling. Oops. I'm jumping around here. Before that, understand the concept of Schottky barriers. How are they similar and different from a PN junction? So the test is not going to be on PN junctions, but in order to understand and compare a metal semiconductor junction to a PN junction, you obviously need to know how a PN junction works. So when I say that the test is cumulative, that's what I mean. You have to understand the previous concepts in order to understand the topics on this last exam. So calculating things like barrier height, built-in potential, I may even ask you to calculate depletion width. Right, so these are some of the main things in the metal semiconductor junctions. If you know the metal and semiconductor, if you know the metal work function and the semiconductor doping, you should be able to tell me what type of metal semiconductor junction you will have. This last one is like more of a practical perspective, right? Most of the time, when we put a metal onto a semiconductor, we would like to make an ohmic contact. When we're doing MOSFETs, for example, we just want to have a contact into the source and the drain. So as a designer, someone might ask you, well, under what conditions will we have a nice ohmic contact? We'd like to avoid the Schottky barrier if possible. So just being able to figure out what the metal and semiconductor work functions are, how that depends on doping. In a certain situation, if you have a certain metal work function, you put that metal on a P-type semiconductor, you'll end up with a Schottky barrier. But if you put it on an N-type semiconductor, you'll get an ohmic junction. So those types of practical questions I'd like you to be able to know. Any questions on metal semiconductor junctions? Is there anything we'd like to go over? Okay, after we're done talking about this, we can go over some of the homework questions. Again, this is not a comprehensive list, but I think it covers most of the concepts. So the main topic on the exam, which will probably be at least half of it, will be on MOSFETs. So what are the things I want you to know about MOSFETs? being able calculate drain currents for an NMOS device and PMOS device in cutoff, triode, saturation. How did the second quiz go? Is that one better now? Okay. It's not due till tomorrow. That's right. That's right. And I actually will have, the quiz will be available for you to take actually until Thursday, even though the official due date's till tomorrow. Okay. But just if you do it, it's a good way to study for the exam too. So you may as well do it. The other thing is, I don't have a quiz on the last set of material. The last set of material is, the second order effects in MOSFETs and threshold voltages. These are things that are on your homeworks. These are things that are on the lectures. Okay. I usually like to have quizzes on all the topics that will be on the exam, but a lot of times we don't have time to have quizzes on everything. So please do make sure that you go through the homeworks very carefully. The threshold voltage calculations can be a little tricky because there's a lot of parts to it, and there's a lot of concepts that you have to understand. So make sure that you're comfortable doing that. And when you do the threshold voltage calculations, be careful not to get into the situation where you're just calculating the numbers and then reporting the numbers. Don't be just a calculator, is what I'm saying. When you calculate the depletion width, if I show you a diagram, you should be able to show me what the depletion width physically means. If I tell you to calculate the depletion charge, you should be able to tell me what physically the depletion charge is. You see what I mean? Like, I want you to relate the numbers that you calculate to actual things on a diagram or actual things on the schematic and what it means in the physical world. Okay, otherwise we could just have calculators do all of our work, right?
So what if your drain power is negative? What does that mean?
If your drain current is negative?
Yeah.
If your drain current is negative, that means the current is flowing from source to drain instead of drain to source. In a PMOS device, the current can flow from drain to source. I'm sorry, from source to drain. Okay, so getting into some of the specifics of MOSFETs. Definitely understand the physical concept of inversion. So in an NMOS device, how the channel region is switched from P-type to N-type. So we went over an example for an NMOS device. I want to make sure that you understand this for both NMOS and PMOS devices. Can everyone see the board okay? All right, good. So what do I mean by understanding the physical concepts of inversion? Inversion of the channel region under the gate. The electric field. The direction of the electric field. All right, what does the electric field do in an NMOS device? When you put a positive voltage on the gate, what does the electric field do? Well, let's start off with which direction is the electric field pointed? Yep, absolutely. It's pointed downwards from the gate into the channel region. So the direction of the electric field, and in the case of an NMOS device, what does that electric field do? It does two things. Right? It pushes holes away. Absolutely. So pushing away majority carriers. And then leaving a depletion region. And then pulling in minority carriers. So we went through in detail the electrostatics of the inversion inversion. Let me open up that. We'll come back to the energy band diagrams in a second. Since we're talking about the inversion. So remember how we derived the electrostatics of the diode, right? We said this is the depletion region, this is the charge density in the depletion region, these are the electric fields in the depletion region, the maximum electric field occurs right at the interface to the P and the N material. We did the same sort of thing for a MOSFET. We showed this diagram here saying we have this buildup of positive charge at the gate, the electric field develops in the oxide, and then you have these electrons that are attracted. These are the minority electrons that are pulled in. These are this is the depletion region that forms when the holes, the majority carrier, are pushed away. And then we actually did the same thing that we did for diodes. We started with the charge density. We have an understanding of the charge density. By integrating the charge density, we figured out what the electric field was. By integrating the electric field, we figured out what the electrostatic potential was. So there's a few key points here if we look at each one of these sections of the diagram. First of all, in the charge density plot, there's just there's a high spike of positive charge here. This represents all the positive charges in the metal here. When we go into the oxide, there are no charges in the oxide under normal conditions. All right, we did talk about an exception where there's something called trap charge. That's if you have unclean processes. So there's no charge density in the oxide. And then this large spike of negative charge density are the blue electrons that you see here. Those are the minority electrons. They're mobile. Those are the ones that are responsible for conducting current between the source and the drain. And then you have the immobile electrons here. The immobile electrons are a depletion region. Those do not conduct electricity between the source and the drain because they're immobile. They can't move. Electricity is moving charge. So this region here, negative charge density, is due to the depletion charge. So I will expect you to be able to calculate the width of the depletion region, okay, and to also be able to calculate the depletion charge. You have the formulas for that here. You need these things to calculate the threshold voltage. But I could just have a question on there for you to calculate the depletion width and depletion charge, and you should be able to do that. I expect you to be able to calculate the semiconductor work function using these formulas for an NMOS and PMOS device. Remember, the semiconductor work function is the distance between EF in a semiconductor and E0, the free electron level. And these are things that you've done before, calculating the semiconductor doping factor, KT over Q, ln of Na over Ni, the substrate doping. So the physics, the electrostatics of inversion, and the physics, I should say the electrostatics and the physics of an NMOS or PMOS device at inversion. Next concept, being able to draw the energy band diagrams in the vertical cross-section for NMOS and PMOS devices at equilibrium, no voltage applied. What are the different modes? What are the different modes we talked about? besides equilibrium, we drew energy band diagrams for the MOSFET at several different modes, right? Let's see if we can remember some of them. Okay, saturation mode. We didn't quite draw the band diagrams at saturation mode. Yeah. I'm sorry? Inversion, right? And then we also drew it at something called accumulation mode. And we also did it at something called the depletion mode. So these were the energy band diagrams in the vertical cross-section. Excuse me. And we also have the energy band diagrams in the horizontal cross-section for an NMOS or PMOS device at cutoff, triode, or saturation. So let's go over real quick the differences between the two. These were the energy band diagrams in the vertical cross-section. So going from the metal to the oxide to the semiconductor. Right. So we showed how you can how to match up the Fermi levels, what to do when you apply gate voltage. The two sides of the diagram change, and then you end up with some of this band bending effects. So this was a device at accumulation. Once you draw the energy band diagrams, I also want you to be able to analyze them. So we said, like, in this case, we're talking about a P-type semiconductor. There's holes in there. We said that there's a slope in the diagram here. So there's an electric field and there's an accumulation of holes within this region called the potential well. So I want you to understand those types of concepts and being able to draw it in the depletion mode and also in the strong inversion mode. So these are the diagrams in the vertical cross-section, going from metal to oxide to semiconductor. Now, we also did the energy band diagrams in the horizontal cross-section. This is going from source to the channel to the drain. This energy band diagram is useful because it allows us to see when the MOSFET will have a conductive channel and when it won't. So looking from the source to the drain, you have an N+ source, a P-type channel, and an N+ drain. So this is what the energy band diagram looks like. When you apply a gate voltage, the P-type material in the middle becomes N-type. So this barrier moves down. And when that barrier moves down, electrons can flow from source to drain. We drew all these diagrams for an NMOS device, but I expect you to understand it for a PMOS device as well, which is why I think it's a great way to study is to draw these same diagrams for a PMOS device. It'll really force you to learn the concepts. So that's why I had this example here. So energy band diagrams in the vertical and horizontal cross-section. And then finally, the second order effects. Body effect. Let's see, the short channel effect, body effect, and tunneling. Gate tunneling. All right, so just as trivia, what does a short channel effect do? How does that change the performance of the MOSFET? It can. The short channel effect can cause a change in the threshold voltage through something called drain-induced barrier lowering. It also it reduces the length of the channel, which increases the current in saturation. So the early effect that you learned about in Electronics 1, that is caused by the short channel effect, short channel modulation. How about the body effect? What is the body effect due to the MOSFET? Which parameter does it change? Changes the threshold voltage, exactly. And how about gate tunneling? Yes, that's when the oxide is too thin. But what performance parameter does the gate does that change? I don't know if we mentioned it, but it's called leakage current. Leakage current is the current that goes into the gate of a MOSFET. In your electronics courses, you always assumed that there's no current going into the gate of a MOSFET. But gate tunneling results in some leakage currents. And those leakage currents can cause the MOSFET to consume more power, as we described in class, because it's drawing some current. So that would reduce the battery life of a mobile device. So these are the main topics here. Oh, and here's the last one. I started working on this yesterday. So this last thing, performance parameters versus design parameters. These will be the toughest questions, but it's something that you can prepare for.
So is the final mainly based on the last chapter?
Yes. It's going to be based on, the final is not going to cover semiconductor junctions. Or it's not going to cover diodes, it's only going to cover semiconductor junctions. The reason I'm bringing this slide up is just to show you this, remind you of this. Most of you didn't like this very much. But I'm showing you this because on the columns you have the design parameters. These are the things that a diode designer has control over: doping, area, and then the material that you choose. Based on those design parameters, you have certain performance parameters like the built-in potential, the depletion width, the saturation current, the avalanche breakdown voltage, Zener breakdown voltage. So this type of thing, although it's not fun to learn at the beginning, because it forces you to really look at the relationships between different concepts, it's very useful from the standpoint of if you actually go into industry and you design diodes. Right? Similarly, so I will have a similar thing for MOSFETs: performance parameters versus design parameters. So the performance parameters, these are the things that would appear on the left-hand column, are things like threshold voltage, the saturation current, the ID at which saturation occurs, the short channel modulation parameter, the depletion charge. The most important of these parameters really is the threshold voltage. Right, that's the one that people care most about. And one more I'll add in here is drain currents. The design parameters, the thing that a MOSFET designer or a fab facility has control over, is the doping of the substrate, the width and the length of the transistor, the thickness of the oxide, and the dielectric constant. And the last thing is whether you use an NMOS or a PMOS device. Right, there's a lot of different knobs that a MOSFET designer can tune, right? So something that has some practical importance is that we've been trying to make the transistors smaller and smaller. Okay, so it turns out that when you make the transistors smaller, you run into short channel effects. When you when you make the transistor smaller, in order to maintain the threshold voltages, you have to change the oxide thickness. So you have to know what changing the oxide thickness will do to the threshold voltage. So designers are dealing with these parameters all the time. In order to reduce the threshold voltages, Intel was increasing the dielectric constant of their oxide layer. They're using high K dielectrics in order to reduce the voltage, threshold voltage. So, I mean, obviously, I'm not going to expect you to know the history of the miniaturization of the transistor and what everybody has done. What I want you to know is, if I change the substrate doping, what will happen to the threshold voltage? If I change the width and the length, what will happen to the threshold voltage? Nothing, right? The width and the length won't change the threshold voltage, but they will change the drain currents when the device is on. So these are the things that I would like you to be able to know qualitatively. I'm going over these things because students always say that the calculation questions are relatively straightforward, but the conceptual questions are always the hardest. Yep.
I looked in a little bit late, just so I can understand, did you say it's only going to be 5 slates in a way?
Yeah, so the 3 main topics, I can post this Word document up to Blackboard after class, and I'm recording the lecture as well, so you can go over it later. But the 3 topics to answer your question is the clean room lab. So these are the topics under the clean room lab, and metal semiconductor junctions, and MOSFETs. I will say that probably more than half the test will be on MOSFETs. Let's say we have like 4 questions. In fact, this is how I'm thinking about doing the test, okay? I'm planning on having like maybe roughly 2 questions on MOSFETs and maybe 1 question on the clean room lab, 1 question on metal semiconductor junctions. Let me add one thing under here. IV characteristics of NMOS, PMOS devices, which are enhancement mode or depletion mode. So if I were to draw the IV characteristic of a device, you should be able to tell me what type of device it is. NMOS or PMOS, enhancement mode or depletion mode. If I draw you the energy band diagram for some device, and I tell you this is what the energy band diagram looks like with a certain amount of voltage applied, you should be able to look at the energy band diagram and tell me what type of device it is. And vice versa. I could say, like, you have an NMOS enhancement mode device, draw me the energy band diagram at accumulation mode. Tell me which direction the electric field points. Tell me what's happening to the majority and minority carriers in the gate region, qualitatively. All right. So let me save this document. There's one more thing I wanted to go over. This is also something that I will upload to Blackboard. This is something I made in a previous semester, but I think this is useful. Rules for analyzing and interpreting energy band diagrams. I think it's best if you write down some of these rules yourselves based on the types of problems you've done, but this is sort of like a reference that you can use. By this time in the semester, I want you to be able to understand some fundamental things. I want you to be able to understand what carriers do in the physical world and then how to represent that in the energy band world. So over the course of the semester, we started with the most basic energy band diagram drawing EC, EV, EI, and then we added in the Fermi level. Then we added in what happens if you have a p-type and an n-type material next to each other. So we described the concept of band bending. And then from there we saw that we have a bend in the energy band diagram. That means we have an electric field. Then we started to think about, well, what are the carriers doing in the energy band diagram? Carriers, electrons go down the slope, holes go up the slope. They cannot overcome energy barriers, but they can get stuck in potential wells. So these were all different concepts that have been sort of summarized in here. So let's go through some of these things. So the first set of rules for analyzing or interpreting energy band diagrams. So first we have the EC, EV, E0, and EF. So at EC, the electrons in the conduction band are loosely bound to the lattice, so they are mobile, they're free to move around. The conduction band is mostly empty, and electrons carry current in the conduction band. The valence band is when electrons that are in the valence band are bound to the lattice. So that's the key difference between the conduction band and the valence band. Electrons in the conduction band are loosely bound. Electrons in the valence band are bound in covalent bonds. The valence band is mostly full. In the valence band, holes carry current, and the holes can move around within the lattice. So those empty, those incomplete bonds can actually move around the lattice the same way an electron can. Obviously, I'm not going into great detail here because we've gone over this stuff before. I'm just trying to draw together a lot of different concepts right now. So if any of these specific concepts confuse you, you can come and see me after the lecture, or you can go back to chapter 2, chapter 3, the lecture modules from there. You can go look at the specifics. Recently, we just learned about another electron level, E0. That's called the free electron level. So an electron in the conduction band is loosely bound. An electron in the valence band is bound in the covalent bonds. An electron at E0 it's that electron is completely freed from the material, meaning the electron can just, it's not connected to the material at all. It can be removed. It's removed from the material. So those are the three different states of energy, different categories. The Fermi level in the energy band diagram, that represents the point where the 50% level, meaning the probability of finding an electron at the Fermi level is 50%. Below the Fermi level, the probability goes to 100%. So below the Fermi level, most of the states are full. Above the Fermi level, most of the states are empty. Right at the Fermi level, the probability is 50%. Okay, the rate at which that probability changes around the Fermi level, remember this, that at 0 Kelvin, the transition is very sharp. Meaning below the Fermi level, it's 100%. Above the Fermi level, it's 0%. That's at 0 Kelvin. But at higher temperatures, the drop-off is more gradual. And that's described by the Fermi-Dirac function. All right, second part, carrier concentrations. We learned that the closer the Fermi level is to EC, the more electrons in the conduction band we have. So the more n-type the material. The closer EF is to EV, the more holes that we have in the valence band, the more p-type it becomes. And if EF is a Fermi level is halfway between EV and EC, this should say EV here. Then the material is considered to be intrinsic. So the different carrier processes. Carrier generation is when an electron jumps from EV to EC, creating an electron-hole pair. Drift occurs if there's a tilt in EC or EV. Electrons move down the slope, holes move up the slope. Remember, a tilt in the band diagram means that there's an electric field. Right, we saw a lot of examples of that when we were dealing with MOSFETs. this was an example of the MOSFET at inversion. The slope in the band diagram tells you that there's an electric field, and the slope is proportional to the electric field. In this case, the slope is positive, right? As you go from left to right, it's an increasing function. The slope is positive. This means we have a positive electric field. Electric field points from top to bottom. So the electrons go down the slope here. That's basically drift, and they get stuck in this region. This is called a potential well. Oops. So the electrons move. Electrons move down the slope. Holes move up the slope. That's drift current. Diffusion current, how that's represented in a band diagram, is where electrons move horizontally from regions of high concentration, in other words, where EF is close to EC, to regions of low concentration, where EF is farther away from EC. So holes similarly move from high concentration to low concentration. We spent a lot of time talking about the energy band diagrams for drift. We didn't spend as much time talking about the energy band diagrams for diffusion, but this is the basic concept here. Recombination, electron drops down from EC to EV, removing an electron and a hole. The tunneling is where the electrons move through a thin energy barrier. We talked about that during the module on semiconductor junctions. Let's just show you that real quick. These were the tunneling type ohmic junction. When the electron sees a barrier like this, normally it won't go over that barrier because this would require the electron to jump into higher energy states and then go over. So that doesn't happen because the electron prefers to go either horizontally or down the slope. However, if this barrier is very, very thin, the electron can actually go right through the barrier. There's a certain probability that the electron will tunnel through that barrier, and that probability of tunneling depends on the width. If you have a very narrow barrier, then there's a higher probability that the electron will be able to tunnel through. So that's tunneling. Then band bending, the slope of the band diagram is proportional to the electric field. A positive slope means a positive electric field and vice versa. The band bending one thing is something that it's best if you practice it. You know, like if you draw the band diagrams of a MOSFET at accumulation, inversion, and so on, you'll see how to do the band bending. And it's slightly different in all the different cases, so it's best if you just practice that. And then the last very important concept is that when we apply a voltage to the energy band diagram, if we apply a voltage on one side of the band diagram, that side of the band diagram goes down. Whichever side you apply the positive potential to, the Fermi level on that side goes down with respect to the other side. So at equilibrium, when there's no voltage applied, EF goes straight across. It's a flat horizontal line. But if you apply an external voltage, EF will be lower on the side with the positive voltage.
If it was negative, it goes up, right?
If it's negative, it's higher. Absolutely. So all these examples that we did when we're drawing the band diagrams and for NMOS devices, PN junctions, they all follow this basic set of rules. All right. So that covers most of the things that I want to go over. Now let's work on questions. So tell me, what kind of questions do you have in the homeworks? What are the kinds of things we can go over? Yep, Michael.
I actually had a question on Module 6 about the flat band voltage. Just
Okay.
the equation.
Sure.
Slide 30 and 39 on Module 6.
Slide 39.
That's just 38.
This one?
Well, that equation there, and they have kind of
derivation of it there on B at the bottom right is
Which one at B?
yeah, B.
Okay.
I didn't understand why it went from the difference between pi m and s down to just equal to the voltage itself, of qi over ci. You see what I'm saying? Like phi m minus phi s isn't in that equation down there. Maybe I'm misreading. So F voltage flat band is equal to the difference of phi m and phi s minus qi over ci, right?
Let's see here.
Maybe you can write it down.
In this, where'd my, there we go. Okay, so this number one up here was showing the situation where you have the metal and the semiconductor have different work functions.
Okay.
And then the example down here was showing showing a situation where they just have an interface charge. So in this example, the metal and the semiconductor work function were the same, but the interface charge was causing. Yeah. It's a little confusing. I'm sorry about that. Any questions about the homework? Yes. Steve.
Just on the notes, it's on the MOSFET. Slide 3, we could possibly go over drawing the PMOS.
Oh, sure. Yeah, definitely. See what's this one. Yeah, so let's draw a PMOS device. Bad idea. All right, so first of all, what does the structure of a PMOS device look like? You have an N-type substrate. And the source and drain contacts are P-type. P+. Why are they P+? You can ask a lot of questions as we're doing this. I think it's good for review. Yes?
So you get an ohmic.
So we get an ohmic contact, right? When we deposit a metal over this, eventually we're going to make a contact here, right? We actually deposit a thin layer of metal over this to make a nice electrical contact. So in order to ensure that metal to semiconductor contact is an ohmic junction, that's why the source and drain regions are made P-type. So this is the oxide, and then this is the gate. So this is what the structure of a PMOS device looks like. Now, in order to get the PMOS device to go into strong inversion, what do we need to do in order to turn the device on? What's the polarity of the gate voltage? It's going to be negative, right? So let's say we make the gate voltage negative. Negative VGS. So then you end up building up negative charge here. You draw this in a different color. So you can see here. Negative charge buildup at the gate. All right, and now what happens due to the negative charge? How about the electric field? Yep, electric field is pointing up. Right? what does the electric field do? How does it affect the carriers, the majority and minority carriers? Okay, it pushes the electrons away, and it pulls the holes in. As a result of that, two things happen. When you move the electrons away, you're left with the depletion region. What is that depletion region composed of? Undo. There you go. So the electric field is going up. So when the electrons, let's talk about this first phenomena here. When the electrons are pushed away, what does it leave behind? Yes? I think I heard. It leaves behind stationary charges, right. And what's the polarity of those stationary charges? Positive, right. So you end up with a bunch of positive charges, but these positive charges are immobile. This is called the depletion charge. Right? And then on top of the depletion charge, the second effect that's happening is that you're pulling in the holes. Those are the minority holes that exist in an N-type semiconductor. And those holes, they collect in this region up here, just right underneath the surface. And those holes are mobile. The region where those holes collect, it's called the potential well, but that region becomes p-type. And when this becomes p-type, now you have a connection between the source and the drain, which is also p-type. Right? So it's exactly the same as an NMOS device. It's just with the polarity switched. So it seems like a lot of you are starting to have an intuition behind this, so that's good. When I learned this material, I don't know if it's just the style of teaching that's changed or if it's what my preference for how to teach this stuff, but like my professors used to always go right into the equations right away, and so it was kind of hard to develop an intuition for what's going on. I want you all to have an intuition for what's happening, to be able to understand qualitatively what's happening, but then also to be able to understand the equations. Okay. What's going on here? Okay, did we cover your question?
Yes.
Okay. Draw the energy band diagram in the horizontal and vertical cross-section. What is the polarity of the gate source voltage? What is the polarity of the threshold voltage? So we've gone over some of these things. We haven't gone over the energy band diagrams. There'll probably be a question on energy band diagrams on the exam, so I don't want to go over everything here. But, why don't we do... I think this is the question that's similar to what you had in the homework. If we do the energy band diagram in the horizontal cross-section, what will that look like? So if we're looking at the band diagram from here going all the way across to here like this. All right. So if we do that, we have just draw it underneath here. We're going to have a P plus material, then we're going to have an N-type material, and then we're going to have a P plus material. So if we qualitatively draw this diagram at equilibrium, we can start off by drawing the Fermi level. At equilibrium, the Fermi level is just a flat horizontal line. For a P plus material, we know that the Fermi level is very close to the valence band, so we can just do something like this. Now this is EC, and this is EV. We also have a P plus material on this side. So the doping levels is the same, so the band diagram will look the same on that side. For an N-type material, the Fermi level is close to the conduction band. So it's going to look more like this. EC is going to be down here, and EV is going to be down here. Now all we do is connect the three. So band bending. Remember, the bands have to be continuous. So this is the band diagram for a PMOS device at equilibrium. So the holes. In a P plus material, we have a lot of holes here. We have a lot of holes here. Okay, holes like to go down. Holes like to go up the slope. All right. So the holes have this energy barrier that prevents them from going between the source and the drain regions. Okay, the source is on the left here. The drain is on the right here. So the holes have no way of getting back and forth. So this is not, the channel is not on. There's no electrical connection between the source and the drain. However, if we apply a gate voltage, as we saw in the above diagram, we switch the material from P-type to N-type. So when the device is on, so equilibrium means like, cut off. So if the device is on, we can also draw the energy band diagram like this. We can draw the Fermi level. We draw the P-type material like this. We can draw the P-type material like this. Now, the way it's going to look in the middle is it's not going to be P plus, so it's going to be P-type. So the valence band will be like something like this. The conduction band will be something like this. Notice that this is the Fermi level is closer to the valence band, so it's still P-type, but it's not P plus. P plus means very highly doped. All right, so the middle here would be P-type. This is P plus. This is P plus. Remember, this is the source. This is the drain. And this is the channel region underneath the gate. Connect these guys together. All right, this is what the band diagram looks like in the horizontal cross-section when the device is turned on. So when a negative gate voltage is applied. Now, one of the points I want to make here, it's an important one, is that when the device is on, remember this is with a gate voltage negative VG. This gate, the voltage is actually being applied between the gate and the body. All right, so that's why the Fermi level here is not. You can still draw the Fermi level as a flat horizontal line. Okay, this is one of those subtle details, but even though you've applied a voltage at the gate, because the gate is not connected directly to the channel, the Fermi level in the channel doesn't change. When you're drawing these band diagrams in the horizontal cross-section, this middle region here, just to reiterate, this is the channel region. This is not the gate. This is the drain. This is the source. So underneath the gate, the Fermi level is, you're not applying a voltage directly to the channel region underneath the gate. So that's why the Fermi level is still a flat line all the way across. So you're not applying any voltage relative to the source, channel, and the drain. You're applying it at the gate, which is disconnected from this region. So if you were to apply a voltage between the drain and the source, then you're going to end up with a situation like this, where you have your Fermi level may be here. And then it's going to be connected like this, and you'll have one of those diagrams which looks like this. Like we saw in the last class period, remember we spent a little bit of time on what happens when you apply a drain to source voltage to the device. So I'm not going into all the details of that, because we did that for an PMOS device already in class. All right, so these are the types of things I would want you to understand. You know, qualitatively, what's happening with the electric field? You know, what's the polarity of the depletion charge? Which way does the electric field point? You know, these types of conceptual questions. In addition, I would like you to also be able to do calculations with MOSFET currents with a PMOS device. So I've drawn some horizontal energy band diagrams. You can expect that there'll probably be some vertical energy band diagrams for an NMOS or a PMOS device, or both. All right. Good question, Steve. Other questions? How did the homeworks go? Are you guys able to do the homeworks okay? How many people are done with the last homework, the MOSFET homework? Almost? Okay. Yeah, I would suggest, you know, do that during tonight, finish this during your study day, so that if you have any questions on the homework or any concepts that don't make sense, you can come to my office on Wednesday and we can go over it. Because, you know, you don't want to save it till the last day, then it'll get kind of crazy. Yes? The threshold voltage is negative for an enhancement mode PMOS device. Yeah, and that one, you know, we can refer you back to this slide here. There you go. So for an enhancement mode PMOS device, the threshold voltage is negative. And when you're doing calculations with NMOS versus PMOS devices, you can refer to this last slide here. This sort of summarizes how the calculations are different for an NMOS versus a PMOS device. Other questions on the homeworks or other parts? Okay, let me just do this real quick then, just for a few minutes before we get out of here. We'll go over, just cover the main points in the homeworks. All right, I'm not going to go over this one because we spent a lot of time last class. It's on the lecture recording, so you can go over that. So the first problem, like I said, these are the types of questions that will definitely be on the exam, and the calculations are not too difficult, but you know, make sure that you're able to do them, because there's always these little details that always end up catching people if they haven't done the homeworks. So a typical question is that I'll give you an N-channel or a P-channel MOSFET with different specifications. In this question, I've given you the difference in the gate, metal, and the semiconductor work function. So I've given you phi ms. Now I could also do a situation where I give you the metal work function, but I ask you to calculate the semiconductor work function based on the doping. Now that's something you should be able to do. Okay, if I just get, for a semiconductor, you just need to know the doping of the semiconductor and the electron affinity, and you should be able to calculate the semiconductor work function from there. Okay, and this problem I just gave you phi ms. So I'll give you the interface charge, the substrate doping, gate oxide thickness, electron mobility, and these types of parameters. The body and source in this problem are connected to ground. If it's not connected to ground, then you have the body effect, and you have to consider the body effect when you're calculating threshold voltage. All right, so when you're calculating threshold voltage, these are the different parts of the equation. A few of the details that I want to point out. The first thing I would suggest is calculating CI. CI is the incremental capacitance. It's the unit capacitance of the oxide layer. It's equal to the epsilon of the oxide over thickness of the oxide. A lot of folks have asked me this, well, where do these numbers come from? 8.85 times 10 to the negative 14, that's epsilon 0. That's the permittivity of free space. When you want to find the dielectric constant of a material, you multiply the free space permittivity by the relative permittivity of that specific material. So this is epsilon r, and this is epsilon 0. Okay, epsilon r is material specific. Epsilon 0 is just a constant, which you've seen from the semester, 8.85 times 10 to the negative 14 farads per centimeter. 3.8 is the relative dielectric constant for silicon dioxide. All right, and the thickness of the oxide, 10 times 10 to the negative 7, is the negative 7 here is because it's given in centimeters. So 10 nanometers is 10 times 10 to the negative 9 meters, but since we have to convert to centimeters, that's why it becomes 10 to the negative 7. So this is calculated in terms of farads per centimeter squared. Now, when you calculate this, the semiconductor work function, EF minus EI, KT over Q, ln of NA over NI, this is a pretty straightforward calculation. This should be volts here, not electron volts. Okay. If it's KT, then it'll give electron volts. If it's KT over Q, it's given in volts. WP, what does WP represent physically? Depletion width. It's the width of that depletion region that forms underneath the gate. The thickness of that layer is the depletion width. When you're calculating this, the key thing I want to point out here, epsilon S. Okay, the epsilon that you use here is not the same as the epsilon that you use in the CI calculation. That's another thing that students often mix up. So this dielectric constant is a dielectric constant for silicon. And so for silicon, you can put in 11.8 as the relative dielectric constant times 8.85 times 10 to the negative 14. That's your epsilon 0. The phi f here is the phi f that you calculated previously. And then the QNA is down here due to the substrate doping. The depletion charge, remember the units for these guys also. The widths will be given in centimeters. Depletion charge will be given in coulombs per centimeter squared. And then when you plug all these different portions of it into the threshold voltage formula, this is what you get. So the little details that I pointed out, please make sure you remember those. And this next part is asking you to calculate the threshold voltage if the body of the transistor is connected to 2.5 volts. So what changes when you connect the transistor to a body voltage? This formula, the depletion width, changes. This phi f that you see here, it changes to phi f minus VSB. Okay, so this is the width of the depletion region without a body effect, 3.5 times 10 to the negative 6. With the body effect, it changed to 6.7 times 10 to the negative 6. So it almost doubled the width of the depletion region. When you double the width of the depletion region, the wider the depletion region is, the more depletion charge you have. The more depletion charge you have, this is going to increase your threshold voltage. Okay, notice that when you doubled the width of the depletion region, going from here to here, you also doubled the depletion charge. This is 5.6 times 10 to the negative 7. This is 1.07 times 10 to the negative 6. So you basically doubled the depletion charge, and that will increase your threshold voltage. All right, then the rest of it is enhancement mode versus depletion mode. These things are quite straightforward. Calculate the drain current when the gate voltage is this, the drain voltage is this. All you need to know is what region of operation you're in, and you know how to do that. We went over this question. You can kind of go over on your own. It's energy band diagram for a metal oxide semiconductor for a PMOS transistor. This is what it looks like at flat band, depletion, and strong inversion. We went over the number 3 in class before. Yep, and I believe that was it. Now, this is the MOSFET homework. Remember that there's also a question on metal semiconductor junctions. You can go over that. So make sure that you understand how to do metal semiconductor junctions as well. Any questions? Okay. All right, then I guess that's it for the review session. Thanks for coming. I'll post this review session on YouTube, so You can go over this again if you'd like. I'll also post the two documents. One is the rules for analyzing energy band diagrams, and the second one is the sheet which covers the topics on the final exam. All right, so good luck studying, and I will see you all on Thursday.
Here on Thursday because I had to be at a meeting, but I just wanted to give this back to you.
Yeah, perfect. Thanks, Steve.